In the grand theater of Cold War aviation, where technological supremacy was often measured in terms of clean sheet designs and futuristic geometries, there exists a machine that defies the typical narrative of progress. We are often told that the variable geometry wing, the swing wing, was the hallmark of the high-end elite, a complex luxury reserved for the likes of the General Dynamics F-111 Aardvark, the Grumman F-14 Tomcat, and the Panavia Tornado. It was the symbol of an era where engineers believed they could cheat the laws of aerodynamics by mechanically altering the shape of the aircraft in flight. But history has a way of subverting our expectations. The most produced variable geometry aircraft in the history of aviation was not a Western marvel of computer-aided design, nor was it the sophisticated Mikoyan-Gurevich MiG-23. It was, instead, a brutal, pragmatic, and decidedly unglamorous modification of a design that was already bordering on obsolescence when the first prototype took to the air. The Sukhoi Su-17, known to the NATO alliance by the reporting name Fitter, challenges the romantic notion that military effectiveness requires revolutionary innovation. Sometimes the most enduring solution is simply to take a sledgehammer to what you already have and force it to work. To understand the Sukhoi Su-17 is to understand the quintessential Soviet approach to engineering: evolution over revolution, ruggedness over refinement, and the ruthless application of brute force to solve delicate aerodynamic problems. This aircraft represents a fascinating geopolitical and industrial paradox. It was a machine built to solve a specific tactical problem, the abysmal takeoff and landing performance of its predecessor, the fixed-wing Su-7. Yet it evolved into a platform of such versatility that it outlived the very empire that spawned it. It served on 4 continents, fought in dozens of conflicts, and remained in frontline service long after its more sophisticated contemporaries had retired to museums. The story of the Fitter is not one of effortless grace or cutting-edge avionics. It is a story of titanium, heat, and the sheer audacity of bolting moving wings onto a fuselage that was never designed to accept them. It is the story of a compromise that became a conquest. The visceral reality of the Su-17 is best captured not in a glossy brochure, but on a cracked concrete apron in a remote airbase. It sits heavy on its landing gear, a long, tubular fuselage that looks less like a carefully sculpted lifting body and more like an industrial pipe designed to channel the violence of its engine. The nose is dominated by a gaping intake cone, a shock-managing center body that regulates the air feeding the hungry fires within. But it is the wings that demand your attention. They are a Frankenstein assembly, with rising fixed intersections that terminate in pivot points, beyond which the outer panels droop and sweep. It lacks the seamless blending of an F-16 or the menacing curves of an Su-27. It looks exactly like what it is, a piece of 50s aerodynamic theory dragged kicking and screaming into the 70s and 80s. When the engine starts, a Lyulka AL-21F turbojet of monstrous power, the ground shakes not with a high-pitched whine, but with a deep, chest-resonating roar that speaks of raw thrust and fuel consumption measured in barrels per minute. This is not a precision instrument, it is a blunt weapon. The genesis of the Su-17 lies in the failure of success. Its predecessor, the Su-7, was a formidable supersonic fighter bomber in the air, capable of dashing at Mach 2 and delivering a nuclear payload. However, it was a disaster on the ground. Its highly swept wings, optimized for high-speed flight, generated almost zero lift at low speeds. This meant that the Su-7 required landing speeds approaching 300 kilometers per hour or more, and takeoff runs that necessitated runways stretching kilometers into the horizon. In a potential European war scenario, where air bases would be the first targets vaporized by tactical nuclear weapons, the Su-7 would be rendered useless, unable to operate from the damaged or improvised airstrips that would remain. The Soviet Air Force, the VVS, demanded a solution. They needed an aircraft that effectively retained the high-speed penetration capability of the Su-7 but could operate from shorter, rougher fields. The engineers at the Central Aerohydrodynamic Institute, TSAGI, proposed the fashionable solution of the day: variable geometry. By swinging the wings forward for takeoff, one could increase the aspect ratio and lift coefficient, drastically reducing the strict runway requirements. Once airborne, the wings could be swept back to slice through the sound barrier. If deep dives into the strategic and technical decisions behind Cold War fighters interest you, subscribe. There are plenty more aircraft worth examining closely. The brilliance of the Sukhoi Design Bureau's approach, led by Pavel Sukhoi, was in their restraint. While the Americans were designing the F-111 with a complex wing that pivoted from the fuselage, necessitating a massive internal redesign and heavy structural reinforcement, Sukhoi took a different path. They reasoned that the main landing gear of the Su-7, which retracted into the wings, was a proven and robust system. Moving the pivot point to the fuselage would mean redesigning the landing gear entirely, a costly and risky endeavor. Instead, they placed the wing pivots halfway out along the span, just outboard of the landing gear bays. This meant that roughly half the wing remained fixed, while only the outer panels moved. This half-swing configuration was mocked by some Western observers as a half measure, but it was a stroke of logistical genius. It allowed the existing fuselage, landing gear, and weapon pylons of the Su-7 to remain largely unchanged, dramatically reducing development time and tooling costs. The resulting prototype, designated S-22I, first flew in 1966, proving that the concept worked. The takeoff roll was reduced by nearly half, and the landing speed dropped significantly. The beast had been tamed, or at least leashed. The airframe construction of the Su-17 series is a testament to the philosophy of durability. The fuselage is a semi-monocoque structure primarily built from duralumin alloys, but with significant use of high-strength steel and titanium in high-stress and high-temperature areas. The rear fuselage, housing the afterburner, is essentially a heat shield, designed to withstand the thermal torture of the engine. The nose section houses the cone-style intake, which contains the shock cone controller. This cone moves forward and backward automatically based on Mach number to position the shock wave optimally for the engine compressor, a critical feature for an aircraft capable of speeds exceeding 2,000 kilometers per hour. The defining feature, the wing, features a massive main spar and a stainless steel and titanium center section box to handle the immense torque and bending moments generated by the pivoting outer panels. When the pilot commands a wing sweep change, a powerful hydraulic motor drives a worm gear mechanism that physically rotates the outer wing panels. The movement is not instantaneous. It is a deliberate mechanical transition that the pilot can feel through the airframe. The wing has three primary settings: 30 degrees for takeoff, landing, and loitering, 45 degrees for maneuvering, and 63 degrees for high-speed dash. Propelling this heavy machine is the necklace of the Soviet aviation industry, the Lyulka AL-21F-3. This engine is widely considered one of the finest turbojets ever produced by the Soviet Union. It is a single-shaft turbojet with a 14-stage axial compressor, giving it a very high compression ratio for its time. While the earlier Su-7 used the AL-7 engine, which was notorious for its voracious appetite for fuel, the AL-21F-3 offered a significant improvement in specific fuel consumption, though it was still a thirsty beast by modern high-bypass turbofan standards. It produces a dry thrust of roughly 76 kilonewtons, and with the afterburner lit, it generates a staggering 110 kilonewtons of thrust. To put this in perspective, this is comparable to the engine power of the much larger F-4 Phantom, but in a single-engine airframe. This immense power allowed the Su-17 to haul heavy bomb loads off the ground with authority, even in the hot and high conditions of Central Asia. The engine's reliability was legendary. It could ingest dust, sand, and debris that would have destroyed a more delicate Western engine and keep running, albeit with a reduced lifespan. Aerodynamically, the Su-17 is a creature of dual personalities. With the wings unswept at 30 degrees, it handles reasonably well, with the slats and flaps on the movable panels providing significant lift. The handling is heavy but predictable, typical of a large fighter bomber. However, as the wings sweep back, the center of lift shifts aft, creating a nose-down pitching moment that the pilot must trim out. At 63 degrees of sweep, the aircraft becomes a true delta-wing dart. It is stable stiff at high speeds, resistant to turbulence, which provides a smooth ride for low-level penetration, a critical trait for an attack aircraft rushing toward a target at 900 kilometers per hour, just 30 meters above the treetops. However, the hybrid wing design came with aerodynamic penalties. The junction between the fixed and moving wing sections generated vortices and drag, necessitating the installation of a large aerodynamic fence on the top surface of the wing specifically to manage the airflow over this joint. Furthermore, the high wing loading, even with the variable geometry, meant that the Su-17 was never a dogfighter. It would bleed energy rapidly in a sustained turn. Its defense was its speed, the ability to light the burner, sweep the wings, and simply outrun trouble. The avionics and systems of the Su-17 evolved radically over its production life, mirroring the advancement of Soviet military electronics. The early variants were rudimentary, relying on simple optical sights and radio navigation. However, the definitive versions, the Su-17M3 and Su-17M4, were sophisticated strike complexes. The fuselage spine was enlarged to a massive dorsal hump to house additional avionics and fuel. The nose cone of these later variants housed the CLEN-PS laser rangefinder and target designator. Unlike Western targeting pods that could swivel to track a target, the CLEN-PS had a limited field of view. The pilot had to point the entire aircraft at the target to obtain a laser ranging solution or to verify a lock for laser-guided missiles. This required immense skill. The pilot was flying a 15-ton jet at nearly the speed of sound, while simultaneously acting as the weapon systems officer, keeping the nose on target while diving through anti-aircraft fire. The navigation capability was upgraded with the PRN-K-54 navigation and attack complex in the Su-17M4, which integrated a digital flight computer, Doppler radar for ground speed and drift measurement, and inertial navigation systems. This allowed for blind bombing runs where the computer would release the ordnance automatically at a calculated point, a capability essential for European weather, where the ground is often obscured by low clouds. One cannot discuss the Su-17 without examining its diverse and lethal arsenal. This was not merely a bomb truck, it was a precision strike platform. It could carry the Kh-25 and Kh-29 families of air-to-ground missiles. The Kh-25L was a laser-guided missile used for destroying bridges and bunkers, while the massive Kh-29, which looks more like a small aircraft than a missile, carried a 317-kilogram warhead capable of penetrating hardened reinforced concrete shelters. For the suppression of enemy air defenses, SEAD role, the Su-17 could carry the Kh-28 and later the Kh-58 anti-radiation missiles, designed to home in on enemy radar emissions. But in the rugged mountains of Afghanistan, it was the unguided weaponry that saw the most use. The aircraft could carry up to 4,000 kilograms of ordnance. This included the ubiquitous FAB series of general-purpose bombs, ranging from 100 to 500 kilograms. It also carried the terrifying S-24 heavy unguided rockets, 240 millimeters in diameter, which flew with the trajectory of a telephone pole and exploded with devastating fragmentation effects. Perhaps the most unique weapon was the SPPU-22 gun pod. These pods, carried under the wings, housed a twin-barrel 23-millimeter cannon. What made them unique was that the barrels could be depressed downwards electronically, allowing the aircraft to strafe ground targets while flying level, or to maintain fire on a target for longer duration during a dive. The operational reality of the Su-17 fitter was forged in the furnace of the Soviet-Afghan War. This conflict became the defining chapter of the aircraft's history and revealed both its strengths and its fatal flaws. Deployed extensively from bases within the Soviet Union and from airfields like Bagram and Shindand inside Afghanistan, the Su-17 was the workhorse of the tactical air support. It flew thousands of sorties, delivering iron bombs and rockets onto Mujahideen positions in narrow valleys and high mountain passes. The pilots discovered quickly that the vaunted navigation systems designed for the plains of Germany struggled in the magnetic anomalies and jagged terrain of the Hindu Kush. Navigation became a visual affair, relying on landmarks and stopwatches. The hot and high conditions sapped the engine's power, increasing takeoff runs and reducing payload. But the variable geometry wing proved its worth, allowing the fitter to operate from runways that would have been impossible for a standard jet. However, the war also exposed the vulnerability of the Su-17 to the emerging threat of man-portable air defense systems, manpads, like the CIA-supplied Stinger missile. The large engine nozzle of the AL-21F was a massive heat source, a beacon for infrared seekers. The Su-17's single engine meant that any hit to the power plant was usually catastrophic. Unlike the twin-engine Su-25 Frogfoot, which could often limp home on one engine with half its tail blown off, a fitter pilot who lost his engine had only one option: ejection. The loss rate began to climb. In response, Soviet engineers rushed to upgrade the fleet's defensive systems. They installed the ASO-2V flare dispensers, initially strapped onto the fuselage and later integrated into huge aerodynamic fairings on the fuselage spine, giving the aircraft a comb-like appearance. Pilots were taught new tactics, approaching targets from high altitude, diving steeply to release ordnance, and then pulling up hard while pumping out flares to confuse the missiles. The psychological toll on the pilots was immense. The cockpit visibility in the fitter was notoriously poor, particularly to the rear. It was like flying inside a bathtub. You could not see the missile launch behind you. You often only knew you were under attack when the warning lights flashed or the aircraft shuddered from an impact. Knowing what you now know about its performance, do you think the design approach was worth it? Share your thoughts below. Compared to its stablemate, the MiG-27 Flogger D, the Su-17 presents an interesting study in Soviet procurement. The MiG-27 was, on paper, the more advanced aircraft. It had a dedicated duck nose for better visibility and a more specialized attack avionics suite. However, the MiG-27 was powered by the Tumansky R-29 engine, which was complex and less reliable in the harsh field conditions. The MiG's complexity made it a maintenance nightmare compared to the tractor-like reliability of the Sukhoi. In the end, while the MiG-27 was retired relatively quickly after the Cold War, the Su-17 and its export variants trudged on. The simple ruggedness that allowed it to survive Syrian dust storms and Peruvian humidity proved to be a quality all its own. The Su-17 also invites comparison to the Anglo-French Seppicat Jaguar. Both were strike aircraft of the same era with similar payloads. The Jaguar was more fuel efficient and had better low-speed handling due to its simpler slat flap arrangement, but the Su-17 was significantly faster, capable of Mach 2 dashes that the Jaguar could only dream of. The Soviet doctrine valued this speed for the initial nuclear strike role for which the Su-17 was originally conceived. Hit the target and escape before the blast wave or interceptors caught you. The export success of the Su-17 family under the designations Su-20 and Su-22 was phenomenal. It became the AK-47 of attack aircraft, sold to nearly every Soviet client state. From the sands of Libya to the jungles of Vietnam, and from the high Andes of Peru to the plains of Poland, the fitter became the backbone of dozens of air forces. In the Iran-Iraq War, Iraqi Su-22s flew grueling missions against Iranian positions. In the conflict between Peru and Ecuador, Peruvian fitters flew combat sorties in difficult terrain. The sheer number of variants, EM, M2, M3, M4, UM3 trainer, speaks to a continuous effort to squeeze every ounce of potential from the airframe. The defining characteristic of the export models was often a downgraded avionics suite, but the core kinematic performance remained. Interestingly, some export customers, like Poland, upgraded their fleets with Western avionics after the fall of the Iron Curtain, attempting to keep the venerable airframes relevant in a NATO-integrated world. This speaks volumes about the longevity of the basic airframe design. It was a structure so sound that it could accommodate technology its original designers could scarcely have imagined. The modernization potential of the Su-17 was fundamentally limited by its intake design. The nose cone intake, while efficient for aerodynamics, meant there was no space in the nose for a large radar. While the MiG-23 and other contemporaries transitioned to side intakes to free up the nose for massive fire control radars, the Su-17 retained its nose intake to the very end. This limited it to being a visual or laser-dependent attack aircraft. It could never become a true all-weather multi-role fighter capable of beyond visual range, BVR air-to-air combat. It carried R-60 air-to-air missiles purely for self-defense. To transform the fitter into a modern multi-role fighter would have required a complete redesign of the fuselage, effectively creating a new aircraft. Thus, its evolution was one of internal systems, better nav computers, better jammers, better sighting systems, rather than a change in its fundamental nature. It reached the absolute apex of what a nose intake, variable geometry design could achieve. Legacy is a complicated word for a weapon of war. The Su-17 did not change the course of history in a single decisive battle. It did not have the glamour of the Top Gun F-14 Tomcat or the terrifying reputation of the MiG-25 Foxbat. Its legacy is one of ubiquity and endurance. It proved that the variable geometry concept, often derided as overly complex and maintenance-heavy, could be made reliable enough for mass production and field operation by conscript armies. It produced a generation of pilots who learned to master a difficult, high-workload machine. The sound of the AL-21F engine roaring over an airfield was the background noise of the VVS for 3 decades. The Su-17 was the tactical sledgehammer that the Soviet Union kept in its belt, ready to smash a front line at a moment's notice. It taught the Soviet aviation industry valuable lessons about the integration of digital systems into analog airframes, lessons that would later be applied to the development of the Su-24 and Su-27. In the final assessment, the Su-17 Su-22 family stands as a monument to pragmatic engineering. It was not the best aircraft in the world at any single task. It was not the fastest, nor the most maneuverable, nor the one with the longest range. It was a compromise born of necessity, a bridge between 2 eras of aviation. But it was available in numbers that mattered. While Western air forces agonized over the cost of their high-tech fleets, the Soviets simply built nearly 3,000 fitters. Quantity, as the saying goes, has a quality all its own. The fitter was the embodiment of this doctrine. It accomplished its mission not through elegance, but through presence. It was there, on the flight line, fueled and armed day after day, year after year. It survived the collapse of the Soviet Union, the changing of borders, and the revolution in military affairs, flying on into the 21st century. Ultimately, the Su-17 leaves us with a profound respect for the engineers who kept it flying. They took a flawed aerodynamic concept and polished it into a weapon of war that commanded respect. They solved the runway performance problem with a mechanical solution that was elegant in its simplicity. They listened to the pilots returning from Afghanistan and bolted on armor and flares, adapting the machine to a war it wasn't designed to fight. The fitter may be retired from the Russian Air Force, but somewhere in the world, in a dusty hangar or on a sun-baked tarmac, a mechanic is likely still wrenching on that variable sweep pivot, keeping the old warrior alive for one more flight. It is a machine that refuses to be forgotten, a variable geometry relic that swung its way into the history books through sheer persistence and hydraulic force. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.